All right, today's lesson is section 5, the fundamental theorem of algebra. So it's obviously very important, but don't be scared. The fundamental theorem of algebra just says if f of x is a polynomial of degree n, where n is greater than 0, f has at least one 0 in the complex number system. Let's just refocus that a little. So it says at least one because it could be repeated. There's always one in the complex number system. That means you can use imaginary numbers with it. The linear factorization theorem. If f of x is a polynomial of degree n, and f of x equals all this stuff for a polynomial where n is greater than 0, f has precisely n factors. It has as many factors, linear factors, as the degree. So that means we can factor it as our coefficient, x minus something else, on and on until we get to our last number. The big thing here is C1, C2, all of those are complex numbers. And a sub n, that number in the front, is your leading coefficient. Remember that complex numbers can be real numbers. They just have a 0 for the complex portion. So, notice how neither of these theorems tell you how to find them, only that they exist. Also note that the n zeros of a polynomial function can be real or complex, and that they can be repeated as many times as I need. So, we're going to find the number of zeros, and then we're going to find the zeros. So this first one, the degree is 1, so that means there is 1 0. To find that 1 0, this is really bothering me that it's not focusing very well. I apologize for that. Our 1 0, well, if I add 2, x equals 2 is my 1 0. For the second one, x squared minus 6x plus 9. Well, the degree is 2, so that means there are 2 zeros. To find those, set it equal to 0 and solve for x. Well, I would try to factor this one first. It is x minus 3 times x minus 3, which means the only 0 is 3. It just happens to be repeated, right? So it has a multiplicity of 2 since it was repeated. All right, for our next one, we have x cubed plus 4x. Well, the degree is 3, so there could be 3 zeros. Well, there are 3 zeros. So I set it equal to 0, and I try to solve for x. For this one, I would factor out an x, leaving me x squared plus 4. And then we have x equals 0, and x squared plus 4 equals 0. For that one, we subtract 4, giving us x squared equals negative 4. And then we square root both sides, giving me x equals positive or negative square root of negative 4. Well, the square root of 4 is 2, and the negative just means it's I. So my zeros are 0 and positive or negative 2i. All right, for our next one, we are going to write this whole polynomial as the product of linear factors and list all of its zeros. We can graph it to start. By graphing, we can guess about 2 of the zeros at negative 2 and positive 1. We can use synthetic division to start breaking this down a little. So I know negative 2 is a 0. Synthetically divide into my original. Don't forget the 0 for the x to the 4th power. I better get a remainder of 0 because I already know it's a factor. All right, I got a remainder of 0. Perfect. Now we know that 1 is also a 0, so I'm just going to take that part, ignoring the remainder section, and divide by 1. Bring down my 1. And if you've forgotten how to do this, you can always go back and rewatch. All right, remainder of 0 again. Perfect. That means now we are working with x cubed minus x squared, plus 4x minus 4. Now looking at this, I can tell that I can factor by grouping. So I'm going to factor by grouping. The GCF of the first two terms is x squared, leaving me x minus 1. The GCF of the last two terms is 4, leaving me x minus 1. So now I have x squared plus 4 times x minus 1. All right, we're almost to our linear factors. The only issue is that, obviously for zeros, this gives me x equals 1. X squared plus 4, we just looked at that one, but we'll do it again. I subtract the 4, giving me x squared equals negative 4. I square root, which gives me x equals positive or negative 2i. So now let's list all of our zeros. Our zeros. We have x equals negative 2, x equals positive 1, x equals positive 1 again, because we had that one twice, x equals 2i, and x equals negative 2i. There's all of our zeros. I didn't have to write the negative 1 twice, or sorry, the positive 1 twice, but I did. It's fine. So now we rewrite our function as a product of linear factors. So I take x minus my first zero, so x plus 2, x minus 1. Since that one happens twice, I can just make it squared. And then I have x minus 2i and x minus negative 2i. There is my answer as a product of linear factors. All right, I think I've fixed the camera a little bit. So conjugate pairs are next. So if f of x is a polynomial that has real coefficients, if a plus bi, where b is not 0, is a 0 of the function, then the conjugate a minus bi is also a 0. So if you have a complex number as a solution, or a 0, the conjugate is also a 0. Remember, we just switched the plus and minus on the imaginary portion. So normally we would say that x squared plus 1 is irreducible. With complex numbers, it is reducible though, because if x squared plus 1 were equal to 0, we would have x squared equals negative 1, and we get x equals positive or negative I. So that means I can factor x squared plus 1 into x minus I times x plus I. If we multiply that back out, we find that it did indeed work. So let's completely factor this. We start by factoring, right? If this was x squared minus x minus 20, we'd easily be able to factor it into x minus 5 times x plus 4. But it's not x squared, it's x to the 4th power. And it's not x, it's x squared. The only thing we change about that is these first terms become x's, or x squareds. And then we factor further, because completely factoring means writing it as a product of linear factors, which means you can only have x's, not x squareds. To do that, we take each of those factors, set it equal to 0, and solve for x. So for the first one, we get x squared equals 5. So x equals positive or negative square root of 5. For the second one, we've solved this one a few times already today. We get x squared equals negative 4. So x equals positive or negative 2i. So to completely factor our function f of x, we take x minus the square root of 5 times x minus negative square root of 5, so plus, then x minus 2i times x minus negative 2i. Here is our completely factored version. The reason we like that is because it tells us every single 0 just by looking at it. Positive square root of 5, negative square root of 5, positive 2i, negative 2i. So let's find all the zeros of this function, given that 1 plus 3i is a 0. We have two options here. We can synthetically divide by 1 plus 3i, or we can use the fact that 1 minus 3i is also 0, multiply, and then long divide. Let's look at synthetically dividing. So I'm going to synthetically divide by 1 plus 3i. And I like to give myself a little extra space when I'm using imaginary numbers here. So I have 1, negative 3, 6, 2, and negative 60. This problem will require a bit of scratch work. So first step, bring down the 1. Multiply 1 plus 3i. Add, I get negative 2 plus 3i. Now we multiply 1 plus 3i times negative 2 plus 3i. This is where I want a little scratch work. So I'll do that right up here. 1 plus 3i times negative 2 plus 3i. I get negative 2 plus 3i minus 6i plus 9i squared. 9i squared is really negative 9, so I have negative 11 minus 3i, and that's going to go right here. Then I add again. 6 and negative 11 makes negative 5 minus 3i. And guess what I have to do now? Multiply again. I'll do that scratch work above it here. 1 plus 3i times negative 5 minus 3i. I have negative 5 minus 3i minus 15i minus 9i squared. So that's really plus 9. So I have 4 minus 18i. Add again. I have 6 minus 18i. Kind of looks miserable, right? We're going to multiply again. 1 plus 3i times 6 minus 18i. Let's go over here. I have 6 minus 18i plus 18i minus 3 times 18, 54i squared. Double check, 3 times 18 is 54. Okay, so that's really plus 54. So I have 60. My eyes cancel. There we go. 60. Add those, and my final remainder is 0. If it's a 0, the final remainder should be 0. All right. But now, if 1 plus 3i was a 0, we automatically know a different one. 1 minus 3i. So I repeat that whole process with 1 minus 3i. Bring down my 1. I have 1 minus 3i. Hey, the nice thing here is that I just get negative 1. So negative 1 plus 3i. Hey, when I add, I just get negative 6. Negative 6 plus 18i. I add and get a remainder of 0. The second time through will always be much nicer than that first time through. So now we are left with x squared minus x minus 6, which we can factor into x minus 3 times x plus 1. Just kidding. We can't factor it into that. We can't factor it into that because 3 times 1 is not 6. Wow, sorry about that. X minus 3 times x plus 2. There we go. So, all of our zeros. First 0 was given to us. It was 1 plus 3i. Second 0 we knew automatically was 1 minus 3i. Next 0 is 3. And the fourth 0 is negative 2. There are all of our zeros for this function. All right, if I have x squared plus 25, to find the zeros, I set it equal to 0. I subtract my 25 over, giving me negative 25 equals x squared. And I square root, giving me x equals positive or negative. Square root of 25 is 5. Square root of negative 1 is I. My zeros are positive and negative 5i. If I wanted to write this out in its fully factored form, I would do x minus 5i times x plus 5i. And then we're done. All right, f of x equals x squared minus x plus 56. My first question I always ask is, can I factor it? Spoiler alert, I can't. So, I will use First, we're going to set it equal to 0, right? I'm going to use the quadratic formula. X is equal to negative b, negative 1 makes positive 1, plus or minus the square root of b squared minus 4 times a times c all over 2a. And now we simplify. I have 1 plus or minus the square root of 1 minus 4 times 56 gives me 224 all over 2. And then we simplify. All right, well, 223. I don't know that that simplifies by anything. I don't know any factors of it, so we're going to go with 1 plus or minus I square root 223 all over 2. And we'll leave it at that. There are our zeros. Now to write this in factored form, I would change it to 1/2 plus or minus I over 2 square root 223 or something along those lines. And then we'd go x minus 1/2 minus I over 2 square root 223 times x minus 1/2 plus I over 2 square root 223. That's nasty. Usually I'll probably just ask you for the solutions on a problem like that. All right, your assignment is not Descartes rule of signs or that. It is a worksheet to go with this section.